keep it simple here, and we're going to just talk about pH, which is the potential of hydrogen. We're going to talk about EC, which is electrical conductivity, and we're going to talk about the nutrient content, and we're going to talk about plant nutrients too. So pH, and I don't want anybody to panic. It's just chemistry is cooking. Let's just think of it like that. So pH indicates the relative acidity or alkalinity of a substance. A pH of 7 is neutral. A pH of less than 7 is acidic. And a pH of more than 7 is alkaline or basic. So vinegar's down here at a pH of 3, it's acidic. And ammonia's up here at a pH of 12, it's alkaline or basic. Each change in number on this scale is a 10-fold change in the activity of hydrogen. So again, pH stands for the potential of hydrogen. It's a measure of the amount of hydrogen. It's reported, because they wanted to make this as complex as possible, as the negative logarithm of hydrogen ion activity. Remember that 1 pH point is a 10-fold change. So we're going to go through this real slow, and I'm hoping that it'll make sense, because it's just counterintuitive. So if you have a pH of 7, in scientific notation, you are saying that the concentration of hydrogen ions in the substance, in this case your soil, is 1 × 10⁻⁷. And if you get rid of that scientific notation, what you're saying is the concentration of hydrogen ions is 0.000001, and that's considered neutral. The 7 comes from the negative of the negative logarithm. So it's a -7, which makes it a +7. That's just the way it works. So that's how you get a pH of 7. A pH of 3 is 1 × 10⁻³ hydrogen ions. And that concentration would be 0.001. So you can see that this is a higher concentration than the pH of 7 hydrogen ions. And this is considered acidic. And again, it's the negative logarithm of hydrogen ion activity. So it's -3, which is +3, and that's why they call it the pH of 3. It's confusing because it's a lower number, but it's more acidic. And lastly, let's go to a pH of 10. Again, that's 1 × 10⁻10, or 0.0000000001 concentration of hydrogen ions. Very, very, very low concentration. So this is considered alkaline or basic. And again, it's a pH of 10 is -10, which is a +10. So the lower the pH, the more hydrogen there is. It's very confusing. So now you're all scratching your heads and you're upset with me. Let's talk about why we should care about that. If you know your soil pH, you can start to anticipate that it may be affecting the availability of plant nutrients and biological activity in your soil. The most essential plant nutrients are available in a pH between 6 and 7. That's when all these things are available. The nutrient availability, the wider this color band is, the more the nutrients are available to plants. So between 6 and 7, most everything's available to plants. As the soils become more acidic or alkaline, you can see that those bands start to pinch down. And it's not that the elements aren't in the soil, it's that the pH is causing them to be in a form that the plants can't easily uptake. Our Nevada soils are alkaline, and they range from a pH of 7 to 9. At those higher pH values, there are certain plant nutrients that become less available. Phosphorus, copper and zinc, iron and manganese, all these things become less available. There's a diagram similar to this one in the chapter on soils and nutrients. So don't try to, rework this. You've got a copy of this. And again, the big question is, can I change my soil pH? No, not really. Our soils are alkaline. And one of the reasons they're alkaline and stay alkaline is they're buffered by limestone. There's lots and lots of limestone that was parent material in our state. And it's not just calcium carbonate as limestone, but some sandstones and siltstones and shales have a calcium carbonate component that cements the grains together. So we're going to explain this real quick. So calcium carbonate, written out chemically, is this CaCO3. And if you add an acid to the calcium carbonate, the limestone, what happens is you get 2 chlorines, a calcium, water, and CO2 gas. And when I was a geologist and I was out doing exploration, I always carried a little bottle of hydrochloric acid with me. And if I was interested, if it had, it was a limestone, or if it had limestone cement and a sandstone, I would put a drop on and see if it fizz. Well, you can do this with your own soil. You can take a teaspoon of your soil and put a few drops of household vinegar and then hold it up to your ear, excuse me, and you can actually hear the soil fizzing. That means you have calcium carbonate in your soil. So I think you can see that if there's lots and lots of calcium carbonate, it doesn't really matter how much acid you add. The acid is never present in the soil. It forms water and CO2 gas. Now, you can try to change pH by adding sulfur, elemental sulfur, but it takes quite a bit of time to lower the pH, and the change isn't permanent because sulfur is very mobile in the environment. It'll move in the soil water, the irrigation water, or the rainwater. You can add organic matter. It takes time and it's a very slow process. You can't add enough organic matter, to change it a full pH point. But as you constantly keep adding organic matter to your soil, you're going to gradually bring that soil pH down. Another chemical property of soil, it's important for gardeners. It's called electrical conductivity, or EC. This measures how well the soil conducts electricity. And it's the salts in the soil that are conducting the electricity. And remember, plants need some salt. We don't want an EC of 0. We don't want no electrical conductivity in our soil at all. Those salts a lot of them are the plant nutrients, the things plants need to grow. If the soil conductivity is very high, it measures how well soil conducts electricity. If the EC is very high, it means you have a high salt content. And then you can be getting into problems because you have salts in the soil that plants don't need, like sodium. And at those high concentrations, high salt contents can interfere with plant growth. So if you've had your soil tested, and if the EC is very high, you may want to do additional testing to see if you have salt-affected soil. Now, to classify salt-affected soils, it's not something you can do at home. You can't even do the EC at home. It's not like the soil texture by field test that we talked about earlier. It has to be determined by several tests. So salt-affected soils are commonly classified for management purposes into 3 groups: saline sodic and saline sodic. And 4 criteria are used for this classification. the electrical conductivity of the soil, the EC that we just talked about, the exchangeable sodium percentage, or ESP, the pH, and the sodium absorption ratio, which is the SAR. So electrical conductivity is related to those soluble salt concentrations like we talked about. The exchangeable sodium percentage is a measure of the amount of sodium on the soil exchange sites. The soil exchange sites, again, that's those clay particles and the organic material that's holding on to those salts. The pH we talked about is a measure of the acidity or alkalinity of the soil, and the sodium absorption ratio is a measure of the amount of sodium relative to the amount of calcium and magnesium in your soil. So if your soil forms a white crust, if it's difficult to get plants to grow, if you know that salty soils are common in your area, you might want to have your soil tested for these 4 criteria to determine if you have a salt-affected soil. Well, what can you do about that? Well, if you've tested and you find you have a salt-affected soil, one of the ways that they suggest to cure it is to flush the soil with water. You want to wash the salt down below the rooting zone. And sometimes the quantity of water you apply should exceed 15 to 20% of what the plants need. And so we pay for every gallon of water we use in a lot of areas. So that's kind of tough. And you have to do that very frequently, low volume irrigations to avoid plant stress. But the problem with this fix is high water tables. So you apply the water, it's not going to drain because your water table is so high. Poorly drained soil, it's not going to move through the soil easily. The water won't move through the soil and take the salts with it. And high content irrigation water, high salt content irrigation. A lot of times they're the cause of or contribute to this high salinity. So what can we do? What are some other things that we could do? You can try to select plants that tolerate salinity. Now, if you have a really, really salty soil, sometimes the plants that will tolerate that salinity aren't plants you really want to grow, like 4-winged saltbush and other things like that. But there are lists of plants that you can find that can tolerate salty soils. You want to avoid excess or salty forms of fertilizer. You want to read on the fertilizer bag what the fertilizer is made from. And if anything says sodium something, you don't want to add that. You don't want to add more sodium to your soil. You can incorporate more organic matter. Remember, you're going to increase the spaces where the soil can hang on to salt, and maybe that will help hang on to the nutrients the plants need instead of sodium. You can add sulfur again to lower the pH, and if it's a serious problem, you can go to raised beds and you really work at creating that interface and getting the drainage that you need, but not wicking the salt up into the raised beds.